Okay. So, section 12-4, we're going to look at the limits at infinity and the limits of sequences. So we're going to look at the limit as x approaches infinity, not as x approaches 0. So we're going to be going out to the right and out to the left and see how we figure out what those are. So, do you remember, and it might be handy if you had your calculator, do you remember horizontal asymptotes? There were 3 rules for horizontal asymptotes. You could tell by looking at fractions tend to give us horizontal asymptotes because the denominator can't equal what? 0. So that means that the function is undefined at that value. And so what happens is the graph of that function will approach that asymptote but never actually hit it, right? So that asymptote tends to be a limit. So let's just look at the first one. So one of the rules for your horizontal asymptote was to look at the degree of the numerator and compare it to the degree of the denominator. If the numerator degree was less than the denominator degree, do you remember what asymptote we had? It's either there is none, or it's y equals 0, or it's a number, y equals a number. Because horizontal asymptotes go this way, so don't they cross the y-axis? Right? And our limits are always at y, aren't they? What the value of y is. So you don't remember, do you? All right, when the numerator is less than the denominator degree, your limit is going to equal 0. Because your asymptote, your horizontal asymptote is going to be y equals 0. So let's go ahead and put this in the calculator because you can tell what's the degree of the numerator? What's the highest degree term? X, so it's to the first power. What's the degree of the numerator, or the denominator? Did I say that backwards? 2, right? So we have 1. So your numerator versus your denominator. Your numerator has a degree of 1. Your denominator has a degree of 2. That means that the numerator is less than the denominator. I can tell you right now the limit as x approaches infinity is going to be 0. So let's go ahead and go into y equals. Use parentheses. So I've got negative 2x plus 3 and parentheses. And then parentheses 3x squared plus 4. And then hit graph. Make sure you have a standard window. Oh, that one looks weird, huh? If you zoom in, okay, so here's what actually happens. Your graph looks like this. My pen is running out. Now on this one, if I shift it over, if I shift my graph, my window over here to the left a little bit, it actually goes underneath the x-axis, but then it goes back up. So it kind of like goes like this.
Can't see it.
So then what happens is, as x approaches infinity, going from that direction, what is the graph actually doing? It's getting closer and closer to the x-axis, which is 0, right? On the left side, even though technically, so if I trace over here, let's see if it'll, I don't think the window will change. So let's see, I want my window for my x to go out to negative 5. Nope, not enough. Window, negative 10. Do you see there where it's getting closer and closer? It does actually dip down a little bit. But as I go further and further out to negative infinity, what is this approaching? What's it getting close to? What y value? 0. And so if I just look at the graph, as x is going in this direction and it's approaching negative infinity, it's also getting closer to 0 because this is going to go down. Like that. That one's kind of a weird one, but the limit is 0. And if you think about this, if I just discounted these numbers because they really aren't important, these are the numbers that are going to make the biggest difference. If I put 1 million in for x, that would be going to the right. If I put 1 million in for x, let's just go to our table. A really big number. 1 million. That's -7 times 10 to the -7. Isn't that a really, really, really tiny number? That's 0.00, that's 6 zeros and a 7, right? And it's negative. Yeah. So what if I put in -1 million? I get 6.7 times 10 to the -7. Again, a really tiny number, isn't it? So they're really, really close to 0. One might be on the negative side, one might be on the positive side, but aren't they really close to 0? And if I keep going out further and further, like let's go out to 2 million, just for chuckle's sake. Let's do 2. 1, 2, 3, 1, 2, 3. So compare that to this one. It's still negative, but it's a smaller negative, isn't it? Getting closer to 0. And if I do -2 million and compare it to this one, we're getting closer to 0, are we not? That one's a little further, this one's a lot closer. So we're going to keep approaching 0 the bigger that number gets. Look at number 2. Numerator is equal to the denominator degree. If you look at this example, my numerator versus my denominator, what's the degree of my numerator? 3. The degree of my denominator? 3. So they're equal. Do you remember what happens in this case? That means that it's going to approach n over d, meaning the coefficient right here of the highest degree numerator divided by the coefficient of the highest degree denominator. So the limit ends up being 2/3. So fix your window so it's back to its standard window. So go to window, fix it. -10, 10, 1, -10, 10, 1. And then go to y equals and clear that out. So put in your 2x cubed plus 6 in parentheses divided by, and in parentheses 3x cubed minus 2. And then hit graph. Do you see the horizontal asymptote right here? Coming through right there? Of course, it's hard to read off your graph what it is, but as I approach infinity, the further and further out I get, it's approaching this asymptote of 2/3. This is the y equals 2/3 asymptote right here. Some of you actually, your calculator actually shows the asymptote, most of you it doesn't. If you want to go into your table and you want to actually put in 2/3, put in 2 divided by 3, what do you get? Huh. Oh, because it's, well, it shouldn't work. Why did that not say error? Did I put something in wrong? It should, right? Am I going crazy or what? 2x cubed plus 6 divided by 3x cubed minus 2? Weird. That's very odd. What if I put in 1? Set your denominator equal to, oh yeah, set your denominator equal to 0. What's 3x cubed minus 2? So it's x is equal to the cube root of 2/3. Try that. That shouldn't matter. What if you put in the cube root? Where? Yeah, I don't know why. Usually I get to put it in. It's not going to let me put it in. Oh wait, I have a cube root. Never mind, we'll get around it. What am I putting in? 2/3? So that's giving my error. Well, I'm going to research why, because it still should be a limit of 2/3 and not the cube root of 2/3. Huh. Fascinating. Well, look at this anyway. Look at your graph. If I were to trace, let's trace on our graph. Trace to the left. Look at your y value. What is the decimal equivalency of 2/3? 0.6, right? So what's happening as I go along? Oops. Is it ever getting, because it's 0.6666666, right? Is it ever actually hitting that, going over it? No. So the limit is approaching 2/3, but it's just getting longer. Eventually I'm going to have all 6s out here because this only has so much of a display. But it is approaching 2/3, isn't it? Okay. All right, so are you okay?
Yeah. Just sounds like she said.
All right, and then if I were you, I would actually draw that on here so you can see that. So draw your asymptote in here as straight as possible. This is y equals 2/3. And then our graph, if we fix our window, our graph looks like this. We do have a vertical asymptote, which don't worry about for these purposes. But we're actually coming close up to that, crossing and going down here. And we're going from here and close coming to that asymptote there. So our limits only pertain to that horizontal asymptote. Then our last rule is what happens if the numerator is greater than the denominator?
Is that what you
No.
multiply? When you multiply that?
You don't.
I thought there was a way you multiplied that.
No. Not. This is the limit does not exist. Only because there's no horizontal asymptote when the numerator degree is greater than the denominator. So on here, my numerator versus my denominator is 2. My denominator is 1, and so that's greater than. So you're going to find that the limit does not exist. So let's go ahead and graph this. It's an interesting looking graph. And you graph these before. This actually has a diagonal asymptote, and you'll see it when you graph it. So go to y equals, clear, and then put in 4x squared plus 6 divided by 8. And I would put the 2x in parentheses, because otherwise it divides up by 2 and multiplies by x. Probably, your calculator will. And then look at the fun graph. Right? Do you see how it has a diagonal asymptote going through here? Well, that doesn't matter for our limits. So, it's going to look something like this. I'll move it in just a minute. So this is what your graph looks like. So as I approach infinity, to the right, what's happening to the value of y? What's happening to this as I go to the right? It's increasing without bound, isn't it? And as I approach infinity from the left, in other words, I choose a number bigger and bigger and bigger from the left, what's happening to the value of y? It's decreasing without bound. And so the limit does not exist. Actually, what the limit is, and you'll find out in calculus that they will accept the limit as infinity, or the limit does not exist. I want you to tell me for right now the limit does not exist. But technically, isn't the limit infinity? Right?
But isn't it calculus?
In calculus, you'll be allowed to say that it's also infinity. But infinity really isn't a limit, is it?
No, it's infinity.
The sky is the limit. Is there really a limit then when you say the sky is the limit? Because where does the sky actually end?
And then you go to space.
Yes, but is there a disagreement there?
I think it's when the universe.
Okay, let's look at these. These are slightly different because they're not one fraction. Okay? So, when you find the limit, and if I were you, I would write the following note to self. So I'm going to put a line right here. Use properties of limits to evaluate. Use properties of limits to evaluate. So if you're asked to find the limit as x approaches positive infinity, or negative infinity, it won't really matter. We're going to break this up. So can't I break this up into the limit as x approaches infinity of the number 5 plus the limit as x approaches infinity of 2 over x? First of all, what's the limit of any number? That number. So I can replace, I know that the limit, because this is really y equals 5, isn't that the line y equals 5? So the limit is always 5, it doesn't vary. As x gets bigger and bigger and bigger, y is always 5. So the limit here is 5, and then plus, what's the degree of the numerator when it's a number? 0, right? What's the degree of the denominator? 1. Isn't the numerator less than the denominator? So what's the limit? 0. So what's 5 plus 0? 5. So the limit of this is 5. I can't remember. I think I graphed this, and I think it does show it. We'll see. So go into your y equals and put in parentheses. You might have to use double parentheses. 5 plus parentheses 2 divided by x and parentheses and parentheses and graph it. Do you see it? Isn't this a horizontal asymptote right there? Now, having said that, I could actually put 5 in here, and I actually get a value, don't I? So it's interesting as to why the limit is 5. Isn't it because those are being combined? Y equals? Did you use double parentheses? Are we good? Yep. Okay. So then let's look at the second one. And I can split that up also. The limit as x approaches infinity of x plus the limit as x approaches infinity of 1 over x. 1 over x, by the way, is no different than 2 over x, right? My question to you is, what's the limit of x? You can't have x. This is the graph. Remember, this is y equals x. This is a graph of y equals x. What does that look like? What does the graph of y equals x look like? Doesn't it look like this? Right? As x increases without bound, what's happening to y? It's increasing without bound. As x decreases without bound, what's happening to y? So does the limit exist? The limit does not exist. So the limit here does not exist. There is a limit here, right? What's the limit here? 1 over x. It's 0 because this is less than this. 0 over 1. So what do you think the answer is? Does not exist. Sounds reasonable, right? So let's go ahead and plug it into y equals. And so we've got parentheses x plus double parentheses 1 divided by x parentheses parentheses. So then look at your graph. Doesn't that look like this one over here? Right? Does that make sense then? And so your limit equals does not exist. Okay, so then we're going to move on and look at sequences. So remember, if I add all these up, even though it's an infinite sequence, couldn't we come up with a value oftentimes? Right? Remember all those sigmas? You love those, right? Okay. Just to let you know that this is a sub n is equal to 1 over 2 to the n. So that's the equation for that sequence. And as n converges, you have to know the word converge versus diverge. So we're going to talk about what that means. So as n increases, and you're looking at n increasing right here without bounds, the sequence converges to 0. As that denominator in the fraction gets bigger and bigger and bigger and bigger, doesn't that fraction become closer and closer and closer to 0? Are you with me? I mean, if I had, I don't know, 2 to the 64th power. Okay. Look at how big that number is, 2 to the 64th power. That would be the 64th term of the sequence. That's a really, really big number. I'd have to move my decimal point 19 places to the right. 1 over that, isn't that going to be super close to 0? Yes or no? Okay, that's what I mean when I'm saying the sequence is converging to 0. The more I go to the right in this sequence, the more that value of that fraction becomes 0. Will it ever exactly become 0? No, because you always have 1 in the numerator. Whereas this one, what's happening in that sequence? Yeah, it's just being multiplied by -1 each and every time, right? So this one, this sequence oscillates. That's your vocab word for the day. It's oscillating. So it oscillates, and therefore diverges. In other words, if it diverges, it goes back and forth and back and forth and back and forth, and you can't determine a number that it's getting closer and closer to. The limit does not exist. So if it's a divergent sequence, the limit's not going to exist. If it converges towards a number, the limit will exist. So let's go ahead and just look at some equations of sequences. Do you still need that? I'm going to get it over there eventually. We good? Okay. So then let's not, I mean, I could sit there and make you go through the sequences and look to see, well, what number do you think it's converging on? But can't we just use the rules above for horizontal asymptotes? Can't we? I have to find the limit. I have to find what number this sequence converges or diverges to. If there's no limit, then it's a divergent sequence, right? So if I gave you something that looked like this as a sequence equation, and then you've got your numerator degree is bigger than your denominator degree, there's no limit, right? The limit does not exist. Wouldn't that be a divergent? According to my definitions here, it would be a divergent sequence. The limit doesn't exist. So I could go ahead and make you run that through the limits, but why when we can use our formulas? So if I were you, I'd write yourself a little note down here. Note to self. See if I can get that higher. Why look at the sequences? In other words, the book makes you write out, the first number in the sequence is, the second number in the sequence is, the third. You have to figure out what all those numbers in the sequence are. You have to run them through the pattern and then look at that and determine what the limit is. Why can't we use the rules above? So why look at the sequences when you can? Use the rules above. So this last part goes really quickly. So let's look at the numerators versus the denominator. What's the degree of the numerator versus the degree of the denominator? They equal, greater than, less than? Equal. So we have numerator equals denominator. When that happens, what's my limit? 2. Why did you say 2? Okay. So the limit is equal to 2 over 1, which is 2. That was a lot easier than looking at the limit sequence itself, right? Or the sequence itself. So then look at this one. What do you know about the numerator versus the denominator? We've got 1 versus 2. It's less than, right? So what's the limit when it's less than? 0. Limit is equal to 0. And if you want to throw it in your calculator to double check, go right ahead. We've done that with 5 problems already. I'm not going to keep doing it with every single problem. And then with this one, they're equal, right? 2 equals 2. What's your limit? Limit is equal to 2 over 4, which is 1/2. Gets closer and closer and closer to 1/2. Well, the degree is 2 equals 2. Numerator equals denominator. All right, so flip it. So now these are the same rules, right? Same rules. Numerator less than the denominator. I just skipped to why do all that work when we can just say, oh, limit is equal to 0, right? So here we have our numerator has a degree of 0, right? Our denominator has a degree of 1. So that's less than, so the limit here is 0. The numerator equals the denominator. Again, that means that your limit is equal to the numerator coefficient over the denominator coefficient for the leading coefficients. So on this one, we're just looking at the 3 and the 5. So what's the limit here? With this. So could my homework be all like this, right? And then for this one, this is the best of them all, right? Our favorite. The limit does not exist. And for this one, we have 3 versus 2 for the numerator and the denominator, and so that's greater. That's it. Any questions?